I mentioned earlier that combustion reactions were also oxidation and reduction reactions. Sometimes, for shorthand, people call oxidation reduction reactions redox reactions. So the word oxidation reduction is abbreviated redox. Don't ask me why they do the reduction part first in the abbreviation. I don't know, it sounds better. Anyway, so I had mentioned earlier that combustion reactions are also oxidation reduction reactions or redox reactions. But if you look at a typical combustion reaction, methane plus oxygen gives carbon dioxide plus water. I don't see any kind of classic metal, non-metal, cation, anion being formed here, but rather these are all covalent compounds. This is a covalent compound, this is a covalent element, covalent compound, covalent. They're all nonmetals coming together, sharing electrons to form these molecules that we call covalent compounds or molecules. So how do I know, how can I look at this and know that electrons have been transferred? Because I told you that it was an oxidation reduction reaction or redox reaction. Well, as it turns out, in the case of ionic compounds, in this classic kind of metal, non-metal situation, it's really easy to tell if electrons have been transferred. It's how the compounds are made. But in the molecular species, it's very difficult. And so what scientists have done in order to be able to recognize oxidation reduction reactions and be able to recognize that electron transfer is occurring is they have devised this method called using oxidation numbers. Okay, and so what you do is you identify, and this is a list of rules, you have this system of identifying oxidation numbers for each element within a compound across a chemical change. And if the oxidation numbers change, that tells you that indeed that particular change is a oxidation reduction type change. Okay, so let me run through the rules and I'll go back and show you how it works. The oxidation number of an uncombined element is always 0. So for example, in the case of these elements, the oxidation numbers would be 0. Okay, now an oxidation number, let me tell you this, is different than a charge. In the case of an element that's just an atom, an uncombined atom element, the oxidation number is the same as the charge. For example, the magnesium has no charge and its oxidation number is assigned as 0. The oxidation numbers for cations and anions that are just elemental cations and anions really are also the charge. That means that that particular ion carries that charge, the same as the oxidation number. But in the case of elements that are in compounds that are covalent compounds, the oxidation number is just sort of a placeholder to say in this compound, most of the electrons are housed on this or the other electron or atom closer to or further away from this particular atom or that particular atom. And so more of the negative charge might reside on that particular atom in that particular compound, but it doesn't physically have the same meaning as literally a charge, meaning an imbalance of electrons on a particular species. Okay, so it's a device, a way to keep track of how electrons are moving around a chemical change, but it doesn't have the same physical significance unless it's actually on an ionic compound with ions. Alrighty, so the oxidation number of an uncombined element is 0. The sum of the oxidation numbers of all the atoms in a species is equal to its total charge. For example, in magnesium oxide, the total charge on that formula unit is 0. So the sum of the charges, which we would call now oxidation numbers, is 0 as well, plus 2 minus 2. The oxidation number of hydrogen is always +1 in combination with nonmetals and always -1 in combination with metals. That's just a rule that you need to remember that helps you assign the oxidation numbers on all the other species in a particular compound. The oxidation numbers of elements in group 1 and 2 is equal to their group number, which is the same as their charge. The oxidation number of halogens is -1, and in ionic compounds, that's really always truly the charge, but unless it's in combination of oxygen or another halogen higher in the group. And then the oxidation number of fluorine is -1 in all of its compounds. So -1 is going to control it to be -1, but sometimes chlorine and bromine and might have different oxidation numbers other than -1. We'll see some examples. The oxidation number of oxygen is -2 in most of its compounds. There's exceptions when it's combined with fluorine, in which case it's going to have a positive value and as a peroxide or superoxide, but we're not going to do any examples like that in this class, so don't worry about it. Okay, so let's practice this. Let's go back now. Using these rules, let's see how this really is a redox reaction by assigning the oxidation numbers. Okay, first of all, they said uncombined elements is always 0. And when we label oxidation numbers, we always put it in a little circle to indicate we're not talking about the actual raw charge. We're talking about this, method that we label different elements within compounds to label their oxidation numbers to detect whether or not they are undergoing electron transfer across their change. All right, the other rule that helps us is the oxidation number of hydrogen is +1 when it's with nonmetals. So in this case, the hydrogen is +1. Okay, now there's 4 of them. So when we go to see what is the oxidation number of carbon, we have to recognize that there's 4 hydrogens with +1 charge. Now carbon can be a lot of different oxidation numbers. It depends on what it's paired with. In this case, it's paired with 4 hydrogens. And the rule is that the total, means the sum of oxidation numbers of all the atoms in a species is equal to its total charge. The total charge of methane is 0. So if the total charge is equal to 0, and I know that I have 4 +1s from the hydrogen, then what, we'll just let X be carbon. What must be the charge on carbon? If you solve for X equals -4. So the charge on the carbon is a -4. Okay, so 4 minus 4 is 0. Then if you move over to this side, the other basic rule that helps keep you straight is the oxygen always has an oxidation number of -2. So I labeled the oxygen, and then based on what the oxygen is, I'm going to figure out the carbon kind of using the same technique. I don't know what carbon is. I know that I have 2 atoms with a -2 oxidation number, and I know the whole thing has to add up to 0. So in this case, the oxidation number is +4. Okay. All right. Whoops. +4. Whoops. 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 Didn't know what happened. +4. Okay. And then in this case, we have water, which is -2 for the oxygen. Hydrogen is always +1, and that just works out. +2 minus 2 equals 0. Okay, so that's how we label oxidation numbers. You're going to have to just practice, look at the rules, back and forth, and practice. So what I'd like for you to do before we talk about, is this a redox reaction? What you're going to be looking for to identify whether or not something is a redox reaction is there a change in the oxidation numbers across the chemical change? And if there's a change in the oxidation numbers, that means electrons have been transferred from one species to another.